Okay, so a student shared a classic problem from Calculus 1 with me today, and we'll sort of just go through and think about the fundamentals of the problem, but leave the solving to the individual student. So, all right, what do they give us? They give us a lamppost, and they give us a man of height 6. The distance between them is 3, the length of the man's shadow is 4, and the man is moving to the right at 5 feet per second. Okay, so far so good. So, before we get into the weeds of the math here, the first thing we want to do is convince ourselves that the one quantity we're being asked to find, what rate his shadow lengthens, is actually a separate concept from how fast the tip of the shadow is moving, right? And uh, you can try to visualize this yourself a little bit, but the idea is that the man is moving at some speed, right? And the shadow is also lengthening. And those two things kind of put together is equal to how fast the tip of the shadow is moving, right? It's sort of that the tip of the shadow, the speed the tip of the shadow is moving, sort of has these two components: the rate the man is moving, as well as the rate of the shadow. So let's think about that a little bit. Let's start by, well, I'll let you solve this for yourself, right? The first thing you want to do is find h, the height of the lamppost, which you can get from similar triangles, right? This shouldn't be anything crazy. You should just be able to solve for 4 over 6 is equal to, what is this, like 7 out of h? Yeah, go solve for capital H and make your life a little easier. But we want to start thinking about the nuts and bolts of this problem, and we want to be thinking in terms of some variables. So the height of the man and the height of the lamppost are constants, so those can be, actual straight up numbers. But let's define L1 as the distance between the two entities, and let's define L2 as the length of the shadow. And L1 plus L2 is the distance between the lamppost and the tip of the shadow. So let's think about what the problem gives us and what the problem is asking us to find. So if we know that the man is moving at 5 feet per second relative to the lamp, that's essentially saying that dl1 over dt is equal to 5, right? That's basically saying that the rate of change of this length right here is 5. Okay, hopefully so far so good. The second thing that we're sort of trying to think out loud here is the derivative of L2 with respect to time. Basically, you know, basically the rate of change of the shadow the man is casting with respect to with respect to time. That's the second thing we're being asked to find. And finally, the derivative of L1 plus L2, let's define that as L3. The derivative of the sum with respect to time is basically saying how much is this total distance L3 changing with respect to time. That's basically the exact same thing as how fast the tip of the shadow is moving with respect to time, right? So L3 dl3 over dt is essentially the last thing that we're trying to find. And we can notice that because the derivative is a linear operator, um, your textbook may or may not use that exact terminology, but it sounds more complicated than it really is. What that means is, if you know that L3 is equal to L1 plus L2, the fact that the derivative is a linear operator means that the derivatives behave exactly like you would hope. So that the derivative of L3 is equal to the derivative of L1 plus the derivative of L2. This is going to be very handy for us. Okay, so what's next? Well, the problem gives us L1, and we know that from this relationship, if we can find L2, or rather dl2 over dt, then we can figure out what dl3 over dt is, right? If you know any two, you know the third. So that basically comes down to the problem asking us to find dl2 over dt, right? That's the crux of the problem. So to do this, I suggest you go set up the similar triangles again and try to think about how to relate L1, or rather how to relate these two terms, dl1 over dt and dl2 over dt. And yeah, if we just sort of look at them, right, we find that L2 over 6, maybe we'll zoom out a little bit. I'll write over here. L2 over 6 is equal to Well, L1 plus L2 over H. And remember that H was something you explicitly solved for, just with similar triangles. So if you have this expression L2 over 6 and is equal to L1 plus L2 over H, at this point, what you want to do is you want to apply the derivative operator to both sides. dt. Sorry, my handwriting's getting a little bit cramped. Right? Apply the derivative operator to both sides. And remember that, again, the derivative is a linear operator, so the derivative of L1 plus L2 is the derivative of L1 plus the derivative of L2. And at this point, you already know what dL1 over dt is, and you just want to solve for dL2 over dt. So at this point, you should have everything you need in order to find this term. Carry out the rest of the algebra yourself, and just remember your basic derivative principles, right? Like this division by a constant, division by 6, or division by capital H, the derivative basically ignores that, right? Just try to remember your basic rules with derivatives. But yeah, this should be able to let you come up with an explicit number for dL2 over dt. And from there, you can return to this expression right here. And now you know dL1 over dt, or dL2 over dt. Sorry, I keep using the word over. It's not really a fraction. That's kind of a notational thing. But anyways, don't let my bad language distract you from the math here. Really, we want to just sum up these two values and figure out what dL3 over dt is, which should be our final answer for how fast the tip of the shadow is moving. Right? And dL2 over dt, the intermediate step, was the rate at which the shadow lengthens. So yeah, go figure out the rest yourself.